Hey guys, Josh is here, and I hope all of you are very excited for this live stream because I really can't hold my excitement anymore to learn more about this very amazing topic from this resource of knowledge that has joined us today called Josh. Josh, I would like to give you a moment to just say hi or whatever to the audience.
Yeah. Hey, everybody. I'm Josh. I'm a software engineer at Snowflake who works on databases and distributed systems. I'm really excited to be here and talk about this to y'all today. Should be fun.
So let's give Josh some love. So whichever city you're tuning in from, just let us know which city you're tuning in from. So you can drop in your city name so that Josh knows that people from all around the world, from different cities, have come here to listen to him talk about the topic that he really loves. And that will really appreciate. That'll be a token of appreciation, and then he will really enjoy it, right? Yeah, he meant like he will really enjoy it. That nod meant that he will
Yes.
really. Okay, so wherever you're tuning in from, you can drop in the city and then we'll show it up on the screen so that Josh feels very motivated. Right. So, okay. So it just started to come in. People are there from Fremont,
Nice.
from Ontario, Canada, from, I think
Awesome.
this means Algeria, from Bangalore, from London, from Houston, from Toronto, from Mumbai, from Brazil. Oh my God, too many people.
Awesome,
Like,
y'all.
how diverse of an audience is this?
Yeah, that's great to hear everyone from all over the world. That's really cool.
Delhi, Frankfurt, Nashville, Chennai, Uttar Pradesh. Okay, I can't keep up anymore. Africa, Nigeria. Okay,
Nice.
guys, thank you so much. I am pretty sure now you feel very motivated. Are you motivated? Or are you nervous more? Like, I want to know what's going on in your head.
Yeah, no, I'm excited. I'm excited. I really like talking about this stuff. It's a really fun field that I enjoy being a part of. So I'm happy to just share that with people and hopefully help
Right.
you all learn a bit.
I'm pretty sure it's going to be like that. Okay, guys. So I think we can start with the live stream now. Um, So, providing scalability and fast computing speed, these are the two major challenges that are faced by developers everywhere around the world. And distributed system solves both of them. Do you feel like it might be a difficult topic to encounter and then cover, but you don't have to be afraid because this resource of knowledge called Josh is here to help us guide through this extremely useful space. So let's know more about All Star Josh. So after graduating from the University of Texas, he has had a enthralling career as a software engineer. He joined He's interned at the top tech companies in the world like Indeed, Google, and Meta. After which he joined Indeed as a software engineer and where he made his way to become the tech lead. And after Indeed, he joined his current company, Snowflake, where he works as senior software engineer working on new database technologies. Apart from all the work stuff, he's a active open source contributor. He contributes and then has contributed to projects like Foundation DB and Apache Curator. He also volunteers to teach coding to underprivileged youth, and he tries to better the society and create an impact in his way. So we are very proud that a person of your technical caliber and the way that you think and then help other people has joined us and as a HackerRank All Star, and then we could not be more happy and excited to do this live stream with you. So welcome to the live stream, Josh.
Well, totally. I'm really excited to be here. Should be great.
Yeah, and the most surprising part about all of it was like, what is your age? Like, if you don't mind disclosing
Yeah,
it.
I'm 29, so you
Yeah.
know, still
So he has
relatively
done
early in my career, but it's been fun so far.
right, and then a lot of it is coming. So I don't know what will happen when you turn 50. The intro will be endless. I don't know, goes on for an hour or something. Okay,
Exactly.
so let's start our discussion for which the audience is here for.
Yeah.
So, but before that, can you tell us more about your story? How did you start and find your interest in this field of distributed systems?
Yeah, totally. So I think where I really got my start was at the University of Texas at Austin. I took a class on distributed systems. My friends told me it was a cool class. And so I thought it would be really fun. It sounded like an interesting field, right? And then I really, during the class, fell in love with it. It was a really cool, just kind of topic for me about like
Right.
thinking about both the theory of how you make large scale systems work and then also the practice that many of the most important or largest pieces of infrastructure in the world for tech companies are distributed systems, right? And then right after that, I got the opportunity to intern on Facebook's data platform team, was called Facebook then, working on their distributed file system. They have the like exabyte scale file system that powered a ton of their data storage at Facebook. So it was a really cool opportunity where I got to like learn the theory and then see it in practice, right, all in the same kind of time span when I was still early in my career. And so then I really knew that that was something I wanted to do. I knew it was a really interesting field. And so then I just kind of continued on that, working on Indeed on database systems and then at Snowflake as well. Again, it's just a really interesting field in my opinion. Like the mix of theory and practice is kind of pretty unique. Like you have to understand like how distributed systems work to build effective ones at, thousands of server scale, like exabyte scale, right? But then also it's very practical because everything uses it, right? So it's a really interesting field that is just really fun to work in my opinion.
Sounds like an amazing story. I'm probably imagining you sitting down in the class and then like you're hearing all of that and then music is going through your head and then you're like, I've found the professional love of my life in some sense,
Yeah,
right?
pretty much. Yeah. No, it's a good class.
Right. Okay. So questions are already coming in. We will take those up. Like, let's just like ease into the live stream. I'll ask your question, Viresh. Okay. So before that, like, can you give us more insight on what your day-to-day work at Snowflake looks like, and what do you think is the best part about your job?
Yeah, no, that's a great question. I think that so kind of two parts. So my day-to-day work at Snowflake is I'm a software engineer, right? So I'm an individual contributor. So most of my day is coding and testing, but also kind of being on some of these kind of complicated projects. A lot of what I do is also like collaborating with other team members. Right? We'll kind of have meetings or write design documents on new features or applications we want to build. And basically, I kind of get to both like help other people build stuff and then also build cool stuff myself. It's kind of most of my day. So a lot of coding, a lot of testing, especially in databases. There's a lot of testing you have to do. It's pretty important to get your database correct and performing. So yeah, that's kind of the high level view. Kind of code reviews, coding, meetings, design discussions, writing documents, that kind of stuff. And in my opinion, the best part about it is I really just the people I work with are awesome, and we get to work on really cool problems. So that's my favorite part. Is it always feels like there's a fun new challenge to solve every day.
That sounds like a very exciting role.
Yeah,
Um, yeah, so good for you, man.
thanks. No, that's pretty good.
Okay, so let's just like take one question that had come in. I mean, so he's currently stuck with multi-tenancy and scalability in an OSS survey for some project. If you could touch up upon it in your talk, that would be amazing. So,
Sure.
do we have something there?
Yeah, so we'll definitely talk about scalability. Because multi-tenancy, it kind of depends on what sort of like tenancy you're talking about. We can definitely talk about that after the talk as well.
Okay, cool. So, Viresh, I hope you will learn a lot from this talk that Josh is going to give us.
Hopefully.
And for everyone else around here, I will be very honest. I am also very new to distributed systems, and I'm pretty sure a lot of you are also very new to distributed systems. So, what we are going to do is we are going to pretend that we are all 12, and Josh has to explain to us some distributed systems concepts, but we have to pretend that we are 12. Okay. So, whenever Josh, explains a concept, all of you need to write down in the chat if you understood it or not. So let's make it more difficult for you, Josh. Okay.
There we go. Well, hopefully they
Okay.
do.
Guys, we are all 12. Okay. And I'm going to give him a few topics and he's going to explain to us. Okay.
Yeah.
So let's start with the first topic, which is distributed systems itself.
Yeah, the distributed systems, very simply, is making multiple computers work together to do something useful.
Okay. Okay. I got that. I hope all of you also got that. All of you other 12-year-olds. If you got that, write a yes. And,
For the
make Josh
understand.
feel like, yeah. No, I'm pretty sure everyone got it. Okay. So let's move on to the next one. That is World Wide Web.
Yes, the World Wide Web it's the internet. It's the kind of connected service of all different websites and applications that you can access over the internet. It's a very large concept.
Okay, cool. I think I got that as well. The third concept being peer-to-peer systems.
Yeah, so in distributed systems, there are a couple models for kind of different ways you design a system. So in peer-to-peer systems, everyone's kind of an equal in the system. They're all doing the same thing, and they're just kind of trying to work together. there's other systems that aren't like that, like for example, a client-server system and distributed systems where each of those processes have different roles or different code they're running or different things they're trying to do, right? So peer-to-peer is just a distributed system where everyone's kind of the same process and trying to do the same thing.
Okay, cool. Yeah, I think I got that. So people are also getting it. People are writing understood.
Yeah,
Yes.
awesome.
So you are going. Okay. Somebody has told that please try to teach in layman terms. Okay. So somebody has not got it.
All right.
It's okay.
Yeah, I'll go from 12 to 5 for the next one.
Okay. The next one he's going to go to 5. Okay.
Mhm.
Cool. Load balancing.
Yeah, so load balancing is if I have many different processes in my system, I need to effectively spread out my work or what I'm trying to do across all those processes, right?
Right. So this was 5-year-old.
Hopefully.
Okay. How about you teach us with an analogy? Like
Sure,
just
yeah.
go negative.
So I guess load balancing, you could say, like, there are, say I'm queuing up to buy a burger at a restaurant, right? And there's several different lines I could get in, one for each cashier.
Mhm.
Making like a load balancer in this case would be someone who's like directing people to lines to make sure that each line is roughly equal and people aren't waiting for a long time, and all the cashiers are getting people to help serve, right? Um,
Right. Makes sense. See, I understood it completely. I hope everyone else as well. Okay, so let's move on to the last one, that is parallel programming.
yeah, so parallel programming is in contrast to single-threaded programming, which is basically just you have one instance of your program running like by itself, right? So parallel programming is you have many instances of your program all running together. Um, and the main difference between like the typical parallel programming model and distributed systems is parallel programming, it's multiple processes on the same computer. Distributed systems, it's multiple processes where each one's on a different computer.
Okay, got it.
And because of
No,
that, there's differences in what you have to consider
no
and what
analogies
you're
for
trying to
this
do.
one.
Yeah, so I guess the analogy could be, let's see. I guess it could be like if you imagine like again, let's go with the restaurant analogy. Like a parallel program could be like the kitchen of a restaurant. Like there's a bunch of people all trying to do stuff together in the same space. The distributed one would be many different instances of the restaurant. Like you have restaurant in different cities or different towns. Like they're all doing the same thing, but it's kind of like people are working at all of them, but it's how the people have to interact with those other people. Right? You have a different interaction with the people that you're in the same kitchen with than you do in the people you're working at the same restaurant but in a different location. Right?
Right, makes
Hopefully that
sense.
makes sense.
Yeah, yeah, it does, it does. And I'm just getting the vibe that you really love restaurants. Is it?
I mean, I do
Is that
like to eat, so
okay? Cool. Right. So I think we can now start with what you have. So
sure.
guys, it's a very top. There's a lot of things to understand. So if you have any questions, you can drop them down in the chat whenever Josh is presenting, and I will ask them to Josh, and then we'll all understand it together. So if you have any questions,
Mhm.
you can drop them down at any time.
Yeah,
Right?
sounds great.
Okay, Josh. All the best. I'm very excited for it.
Yeah. All right, so let's go ahead and get started. So, kind of like what Sanskar was saying, to hopefully make this talk, reasonably accessible to the general audience, because obviously distributed systems can be a very deep topic. What I want to talk about is kind of what, in my opinion, every software engineer should know about distributed systems, right? What's kind of generally useful concepts you can take
Right.
and apply to whatever software you're building, whether it's a full stack application or anything that you want to build, right? Um, So just to kind of give you all an overview of what we're going to talk about today, first we'll just do a bit of an intro to talk about, some theory and some basic concepts we can use to kind of talk about the rest of the content. And then we'll talk about two different types of systems, stateless distributed systems and stateful ones. Then we'll basically just have some, time for questions at the end. So to do an intro, we already kind of did this, so I'll just really briefly go over the slide. But so I'm a database and distributed systems software engineer. I've worked on databases and storage technology at companies like Snowflake, Indeed, Meta, and Google, and I've contributed to open source projects in this field like FoundationDB, Curator, Hadoop distributed file system, and other things like that. And so the reason why I thought that this topic would be important for the wider audience is distributed systems are really powering the world as we know it today with technology. right? Obviously, the internet, as we talked about, is a distributed system. Like everything we do on the web, like think about how much you use your phone in the web. All of that is a distributed system, right? And then there's also several things that are kind of powered by like distributed data systems specifically, right? There's so many things today in society that are powered by like large data analytics or by machine learning, right? And those things that are all things that require like large scale distributed systems to, specifically machine learning, for example, to train your models and to analyze the data that then becomes the machine learning, features and applications that you use in your daily lives. Some other examples, just kind of more interesting societal ones, are like multiplayer video games is a good example of how, distributed systems has really entered the kind of entertainment industry, right? And then blockchain is an interesting example of how like the distributed system itself has kind of become a mainstream, like talked about part of society, right? So, and then kind of to carry on this point, in today's age, with the internet age, pretty much all the software you write will be part of a distributed system, right? There's very little software we write nowadays that's just running on one device, not talking to any other devices, doesn't call any other APIs or anything like that, right? So I think that because of this, really understanding the basics of how these systems work and how their concepts apply to what you're doing will really help you build more scalable, more performant, and more reliable systems. So, and I'm going to assume some base level of like software engineering tech knowledge, but hopefully this is pretty accessible to that wider audience. Cool. So then I wanted to talk about just some basic theory that will really help us like lay a foundation to understand some of these concepts as we go forward. So I keep using this term distributed system. We defined it for 12-year-olds, but now the kind of definition for y'all I want to give is that a distributed system is a computing system that consists of 2 or more processes that run on independent computers and that communicate by passing messages to each other over a network. And so some of the things that make this challenging is in this field, what we're really trying to do is to build a reliable system out of unreliable components, right? In this system, individual processes can fail and crash, and the network can also be unreliable. Like I'm sure many of y'all have experienced, losing cell service, your router going down, like some sort of technology like your phone, your laptop or something not working, right? Like this is just the nature of technology, right, is that it can be unreliable. And so we want to build a system on top of that is reliable. And kind of the other challenge of distributed programming specifically is when your software is all running on multiple computers, there's no shared state between them, right? The only way they can share stuff is by passing messages to each other. And then one of the complications of this is there isn't a global clock either. What this means is that each computer has their own idea of what time it is. And so you can't always even tell, like, if 2 things happen, which one happened first. On any single system, that's obvious, but in a distributed system, it's actually impossible sometimes to know, which makes things, even just basic reasoning about what's happening in the system, difficult, right? And so because this is difficult, what we wanted to do in this field is kind of define models or ways to think about what can happen to your system, right? So we call some of these fault tolerance models, which basically just means how does my system tolerate the fault or the failure that can happen? And so like the simplest one that we usually think about is crash failures. So, assume I have a distributed system. I have my programs running on, some number of different computers, right? At any point in the crash failure model, these programs could just stop executing, right? And this could, in real life, model, say, power failure or a computer crashing, right? But this can also model things like, a bug in your software, like if your software runs out of memory or has like a segmentation fault that causes it to crash. This models that type of behavior, right? Then on top of that, we have network failures, which basically means if 2 processes are sending a message to each other, that message might either just never make it, or it might be delayed by some amount, right? And interestingly, we consider this like a hierarchy, where network failures kind of encapsulate or include crash failures. Because from the other processes in the system, if they can't talk to another process, it's not clear to them necessarily whether that's a network failure or a process crash, right? You could consider a process crash a single host, like network partition, essentially. And then kind of the final model to mention is arbitrary failures or Byzantine faults, which basically, colloquially, probably the best example is like getting hacked, right? But this also includes things like software corruptions or bit flips, or basically anything that would cause your program to not do what you programmed it to do, right? And so this is interesting because this was basically just a research area for decades up until the advent of blockchain, when it kind of hit more of the mainstream. But in practice, like Byzantine or arbitrary faults aren't really handled by most practical software systems, and most research is not focused on that area. So today, to keep it simpler, we're going to talk about just crashing network failures and the systems that are built to handle these things. So throughout kind of the rest of today, what I want to talk through is just like an example application someone might build, right? Say a full stack app. Like your full stack app's going to have, a client who's using the app. They're going to go through like a load balancer, then you have the web application, and then your web app's going to talk to a database, right? This is a very simple, very theoretical, high-level application. No languages or code or anything, but just kind of the architecture of what that looks like, right? And so when you're a full stack developer, the code you're usually writing is the client and the web application, right? Your code is going to use other services, like you're going to have a load balancer, you're going to talk to a database, there are other services involved, right? But the code you're writing is not those services, you're just integrating with them. So that's kind of the intro. Now I want to talk about stateless distributed systems, which is basically the subset of systems that are distributed that do not maintain or manage any sort of persistent state, right? And this is in contrast to stateful systems, which do, but we'll talk about them in a sec because they're basically the same thing but more complicated. So in our example application we were talking about, the stateless components of this are the load balancer and the web application, right? A client may or not be stateful, right? Sometimes you store stuff in browser local storage or on device, right? And your database is certainly stateful. That's kind of the point of a database, is to hold data, right? So when we're talking about stateless systems, there are a lot of challenges and interesting topics, but I think two of the most relevant are load balancing and failure detection. So load balancing is basically we have this distributed system with a bunch of processes in it. We want to actually use all our processes and spread out our work or requests or whatever we're doing across all of them, right? Like it'd be a pretty useless distributed system if we had 100 servers running and only use one of them, right? And then the other side of it is, as we saw, like processes and networks can fail. So in our system, we need to identify when that happens and react to it to be able to keep our system reliable, right? So to go through these topics, I want to, again, use this as the example of our web application, right? Say we're building a web application. Our application is going to have an API, and we're writing that application code, right? So say we have our application written, we want to deploy it and have people start using it, right? So we're going to deploy it first to just a single instance of our web app, right? And that may work okay, but there's going to be some problems with this. So number one, like we talked about, failures. If we're just running one web application and that application crashes or the host becomes unavailable, our entire website's going to be down, right? We can't access the service that application is trying to provide. And then another thing is, say we had one app for a while and it was working fine, but then our site got really popular for some reason. Now our increase in traffic may not be able to be handled by a single instance of our web application, right? So the solution to this is just to add more. Now we have many web applications, right? But then this brings up an additional problem, which is now that we have these web applications, how do we choose which of them to send our client requests to, right? So this is what a load balancer does. If you're not familiar with it, a load balancer is basically just an application that will take incoming client requests and forward them to many or any of our application servers that we have, right? And it's called a load balancer because it wants to balance the load, right? And so some examples of these technology you may have heard of are Nginx, HA proxy, there are a bunch of other ones, but these are some common ones. And so to really understand, though, what load balancers do and how distributed systems is relevant here, what I want to do is let's put ourselves in the shoes of this load balancer. Like say we're building a load balancer, right? What does our application need to do? Well, it needs to balance the load, hence the name. We need to take our requests and evenly distribute them across our web applications, right? If we were only sending them to one of our 100 servers, it's not a very useful load balancer. And then the other side of it, we need to handle failed or slow servers, right? Since any of our web applications could fail at any point, we need to identify that and send our traffic to a different server, right? So that clients don't see interruptions or unavailability. So first, let's talk about load balancing. How does our load balancer distribute the requests amongst application servers? So to make this problem a little easier, instead of trying to think about the big picture, what I want to do is just think about one individual request, right? One request comes into the load balancer. Which server do I pick for this request, right? It's kind of a simpler way to think about it. So some basic examples of what we could do are we could just, pick a random server, right? This is not the most ideal, but it does work pretty well. It'll, reasonably equally distribute load across our servers. Or we could do something like round robin, right? Where you alternate which server you send the request to in a specific order, right? And so this is guaranteed to evenly balance the number of requests over some period of time, right? But unfortunately, this doesn't work perfectly. There are some problems with this. Namely, that not all requests are created equal, right? So again, let's try and put ourselves in the shoes of someone. This time, let's say I work at Twitter, right? If I consider requests coming in to load a Twitter feed, there's probably a big distribution to those. Specifically, you can imagine that if someone follows 5,000 people on Twitter and they want to load their feed, that's probably a more expensive request to do than someone who follows 5 people, right? You probably have to read a lot more state from the database. There's a lot more HTML you have to render. There's a lot more computation you have to do, right? Like it's probably a lot more expensive to do that big request than it is these smaller ones, right? And this is true of many systems. Not all requests that come into your system, do the same amount of work. And this is especially true if the same web application has many different types of requests you can do to it, right? Could be if you're loading your Twitter feed and like posting tweets to the same application, those are very different things your system needs to handle, right? So then because of this, I want to walk through an example of how this can be bad. So in this example, we have our load balancer, we have our 2 application servers, and we're going to use our round robin algorithm to pick the next server we're going to send each request to, right? So in this first case, we have a request come in, we're going to send it to the first server, and then we're going to move our round robin pointer so that the next request goes to the next server, right? So now, great, we've evenly distributed our load. We balanced it, right? But then here's the problem. If request 1 was the expensive one and request 2 was the non-expensive one, request 2 might complete first, right? So then we get another request. Now we're going to send them new requests to the server that already has work, not to the one that's idle, right? And so you can see that this is suboptimal. We're not distributing our load. We're not balancing it effectively, right? And so you can imagine that a solution that did this might, instead of just always doing the next server, might have wanted to inspect the state of the system, see that server 1 already had a request and server 2 didn't, and send it to server 2 instead, right? So that's what the least connections load balancing algorithm does. It's also known as a join shortest queue. But basically the idea is, as my load balancer, I know how many requests I've sent to each of these servers, right? And specifically, I know how many requests I've sent that have not yet received a response. This is also known as how many outstanding requests there are, right? How many requests is a server currently processing? So very simply, I choose the server that is currently processing the lowest number of requests and send it to that one, right? And it turns out that this is pretty much optimal for the single load balancer situation, right? You can basically find the least loaded server and send traffic to that. But there is a problem here, and that's if you have many load balancers, right? Because then each load balancer knows its local state of how many requests it's sent to each server, but it doesn't necessarily know the global state of how many requests each server is processing, right? So if say we had this example, we had 4 load balancers that all had sent this many requests to each of these servers. They're all going to pick the middle server, right? So even though that is currently the lowest loaded one, they might then flood that server with new requests, causing those requests to be slow. This is an example of what's known as the thundering herd problem, which is basically a large amount of traffic kind of goes to one point in a particular amount of time. And so to handle this, if you have many load balancers, the algorithm you want to use is the random 2-choice algorithm, which seems worse at the start than the least connections. Basically, you just pick 2 servers and send the request to the one of those that has the least connections instead of examining all your servers. And so it seems like this should be worse, but it avoids that thundering herd problem because not all the servers are even going to consider the same, or not all the load balancers are even going to consider the same set of servers to send their requests to. And it turns out this is pretty much almost as optimal in terms of finding the least loaded servers to send requests to, but then avoids that thundering herd problem. So if you have many load balancers all going to the same application servers, you might want to consider this approach.
I had a question. So the
Yeah.
one that you spoke about, the third, when there's just one load balancer, it's called LSQ, if I'm correct. Like,
Yeah, it's
that,
least connections or join shortest queue. The join shortest
right.
queue is like the queuing theory name for it. Least connections is like the load balancer name for it.
Right. So like, what's the trade-off here? Because it sounds better than the previous one. So does it
Yeah.
take more time to execute, or is
No,
it
you just want to use this instead of round robin or random. It's strictly better.
okay? So
Yeah.
everyone like generally goes for this one, or
Yeah. So
uh,
basically, generally, I mean, load balancers, you can kind of, like, for example, Nginx, you can configure this like 4 or 5 different options for how to route requests. Generally, if you have one load balancer, you'll configure this one. If you have many, you'll configure this one.
Makes
And
sense.
it just basically depends on your deployment, right? Like, you know how many load balancers you're deploying for your app, and so you can kind of pick. I believe the default for Nginx is this random two-choice one because it still works pretty well, even if you only have one load balancer, but then it's the best thing to do if you have multiple. But yeah, so basically you
Makes
don't ever want to use round robin or random. They're just strictly worse. But I wanted to give them as a simple example of like, what's the first thing you could think of, and then why does that not work, right?
Makes sense.
And then there's kind of one other thing to talk about here, which is sometimes what you'll also do is you'll kind of almost assign each client to a server, right? So I could say based on the IP address the request is coming from, I'm always going to send requests from that IP address to the same server, and there are sometimes reasons you want to do that instead. So that was kind of an overview of different load balancing algorithms. We talked about how this specifically applies to client-server models, but the general problem of spreading work equally across your distributed system has many of these same principles, right? So then the other thing to talk about, which applies to all distributed systems, is failure detection, right? Since processes can fail, how do I know when they fail, and what do I do about it, right? So again, let's say we have the example where we have a single load balancer, and let's just consider one of our application web servers, right? The normal case is a load balancer will get a request, send it to that server responds successfully, and then we're all good, right? But sometimes that server may respond unsuccessfully, right? It could send us an error back instead of the successful response. And in this case, you might want to consider, there might be a problem with the server. Maybe I should send my request to a different server instead. But the even more difficult case is, what if my load balancer sends a request to that application server and it just never responds? Now we're kind of in a bit of conundrum, right? We can either wait for it to respond or retry the request to a different server. And this makes it difficult because if it's just like a network blip, or the process is actually processing our request and is just about to respond, we don't want to send the request to another server. We just want to wait, right?
Yep.
On the other hand, if the process is dead or there's some sort of network issue, we need to send the request to a different server because this one's never going to respond, right? And the problem here is that just based on sending a request and not having heard a response, we have no idea which of these states it's in, right? And so in distributed systems, this is known as the indistinguishability problem, or not being able to distinguish or tell what state you're in, right? And the problem here is specifically that there's a bunch of states we could be in. In some of them, we need to do one thing. In others, we want to do a different thing, right? So this puts us in like a bit of a conundrum. It's like, what do we do? And there's actually not a perfect answer to this. The fact that a process could be dead or just slow means that in general, consensus and failure detection are actually impossible in distributed systems. So what do we do? We'll give it our best effort. So that looks like, there's kind of two common approaches for this, is to basically, one is you could set a timeout on your request, right? Where you can basically say, if this hasn't responded for 30 seconds, it's very likely that it's just not going to respond. Let's try a different server, right? The other is you can add what's called a health check to your server, which is basically you add a separate API to your web application that is very, very simple. The API is someone asks it, are you alive? And it responds, yes. And that's all it does. And the reason this is useful is because, well, usually you run this at a high priority, and it is a very simple operation, right? And what this does is it basically checks that all of the properties of what are needed to be a member of a distributed system are present. The host is alive, and it can send and receive network messages, right? So then if your health check succeeds, this is still a member of your distributed system. If it doesn't, it's likely, because it's such a simple operation, that the host is either very slow or not present in your system, right?
Right. So we have a few questions. Like, do you want to take them up before we
Sure.
move forward?
Yeah, I can do that.
Okay. So how do we know if we need more load balancers or more servers to take care of the load from a web application?
Mhm.
And are there any tools or techniques for this one?
Yeah, that's a great question. So I think the general way you want to approach this is just monitoring your production environment. Like, what you'll often do when you have these systems deployed is you'll have metrics about your system, right? You'll be able to look at each of your application servers and see what's their CPU utilization, how many requests do I have outstanding to this server, right? And that kind of thing. And then what you see is either if your CPU gets saturated or you see a huge amount of requests outstanding that aren't responding, that generally indicates a problem. Same with request latency. You want to monitor the latency of your requests, right? And if you see that going up, there might be a performance problem. But then the latency increasing might not necessarily be because of your application servers or your load balancers. That could be also, say, a database problem, right? So you need to have metrics at every level. You need to have metrics on your load balancer CPU and requests. You need to have metrics on your application server CPU and requests and queues, and you need to have database metrics, right? So you can monitor kind of all of these things, and that'll give you a good idea of the overall performance of your system, as well as the individual components. And then based on that, you can make decisions. Right? This can either be done manually, like you could basically just look at your on-call person or your ops engineer will look at it, say, all of our application servers are consistently over 80% CPU. We need to add more. Or what you can do even better is, especially in cloud providers, you can use auto scaling, which is basically you can set a rule that says, if all of my application servers are over 80% CPU utilization, tell your cloud provider to add more, right? And then it'll automatically register in the system, and then load will be balanced across all of them. And you can do similar things to reduce it too. Like if you have like 10% CPU, you can tell your cloud provider to take some of those servers back, and then you'll pay less for it because you don't need them. Now, hopefully that answers your question.
Right. So Flavius or Flavius, I'm not sure if I'm saying it correctly, but he also answered this question saying that
Yeah.
you need only one pair of load balancers per geographical region, but most companies are fine or even desired to be tied to a region only.
Yep.
Like, do you have anything to add to that?
Yeah, I think that's pretty accurate. Like load balancers are very efficient systems. So unless you have like a really, really high scale application, you generally only need for performance one or a couple, right? And as Flavius mentioned, generally many companies also have different regions around the globe where they have systems, right? Like if I'm in the US, the network latency to say India is hundreds of milliseconds, which is noticeable to a human, right? So what companies will do is they'll have many copies of their applications deployed around the world. And then so what you do when you access that site is first DNS, your domain name service, is going to translate the IP address to the data center that's closest to you, right? And then within that data center, it's going to forward it to one of the load balancers. And then that load balancer is going to pick which application server to send it to, right?
Okay, so we have another question. So this assigning is sometimes referred to as affinity. Uh,
Yeah, thanks, Ashish. Yes, that's exactly correct. The affinity is what that's known as, and you can do it for client affinity. There are also other systems where you can basically like you want to send different types of requests to certain servers, in a sticky way. Yeah, so that's correct. That's the name of that. Another name for that concept.
right. Okay. A lot of questions are coming in. What is the threshold for capacity planning?
That's a really hard question to answer in general. I would say it basically depends on your system, but there are some kind of common rules that apply pretty well. Like for storage systems, I think like when you're looking like disk capacity, you generally want to have like anything. It depends on the system again, but I've seen anywhere from like 60% to like 80% is when you want to start scaling up. The same with CPU, because I guess the overall concept is your traffic's not going to be completely uniform over time. It's going to have ups and downs with like daily traffic or weekly traffic or even like yearly. There's going to be bursts when people use your site, So like generally what you want to do is you want to have enough to handle bursts, like have just enough to handle bursts while having enough to sustain your kind of regular load, right? It's kind of the one rule of thumb, but it's up to you to monitor your application to know what those thresholds are, and also up to you to kind of know what the behavior of your application is and the nature of your traffic is, right? Like different applications have different cycles of traffic and different bursts and that kind of stuff, right?
Makes sense.
Hopefully that makes sense.
I hope that answered your question, Susmita.
Yeah.
The next question we have here is it possible at all to add a load balance to a WebSocket connection?
Yeah, so with persistent long-lived connections like this, generally the only thing you can do is load balance at the on connection, because then it needs to be persistent connection, right? But what you can do if you have a problem is generally you can just, if like your application needs to handle that disconnecting anyway, right? So what you could do is you can just, if you have a really big problem, you can close some of those connections and reopen them on a separate server, and the client application has to handle that. It's not ideal for performance necessarily, but you can still kind of do some of these things.
Makes sense. Right.
Cool.
Okay. Yeah, I think we can move. Okay, let's take one more question and then we'll take the other questions after like a few more slides.
Sure, that sounds good.
Right. So this assigning of application server. Okay. So I think we've
I
already
think you
asked.
asked that question. Yeah. Similar question. Yeah.
Yeah. So can you talk a little bit about leader election and handling failure? What algorithms do you recommend?
Yeah, thanks, Paolo. So that's a good question. That falls more under the purview of stateful systems, or what's leader election is technically stateless. But yeah, so basically, what Paolo, leader election is an algorithm in distributed systems where basically I have a bunch of different servers and I need one server to kind of coordinate everything, right? And the reason you want to do this is because making decisions can be expensive between multiple servers. So it's kind of a way to break it down where you don't need to make a decision for everything you do. You just need to make a decision about who is making the decisions in your system, right? This is kind of like electing a president in a democracy, right? If you had to consult every person in the country for every decision anyone in leadership needs to make, it's not scalable, right? So you appoint someone you trust to make those decisions, and then they make the decisions, right? But that means you need to be able to trust the process of electing that person. That's what the leader election is. So in distributed systems, this is typically done with like a consensus system, like Paxos and Raft are examples of this that are typically used to do leader election and consensus.
Makes sense. Okay, I think we can move forward now. The other questions we will take it after a few more
Yeah,
slides.
for sure.
You're good.
Awesome. So let's keep going. So this is basically wrapping up the stateless systems section. I think just kind of the key points to take away from this when you're building whatever system you're building is you want to understand your request behavior and distribution, like we saw, like what types of requests are in your systems, what resources do they need, how do they interact, that kind of stuff. You also configuring health checks is something you just pretty much always want to do. And you want to choose your timeouts wisely as well, right? Because if you consider the case of I'm sending a request to a server and it hasn't responded, a too low timeout might make it so that the request was just about to complete, but now I marked it as failed, right? But on the other hand, a too high timeout might be if there's a request that's not going to complete, I'm just sitting there waiting for no good reason when I should send the request to another server. And what makes this difficult is you as the application developer are probably the best person to determine what a reasonable threshold for that is, right? There are certain systems that can sort of do it automatically, but it's not a perfect art. And then I think the other big thing is to understand that failure detection, as we saw, is not perfect or immediate. Like if something fails in your system, it's inherently going to take the system time to react to that. So you're always going to have, network failures. You're going to have like some requests that fail and have to be retried. You're going to have slower requests when something fails. You really can't get around that. So they're kind of some takeaways that hopefully help you build more reliable applications, especially in this space. So next I want to talk about data storage systems or stateful distributed systems. And so this is the field I work in. It's a very deep topic. So again, I kind of wanted to focus on what I think is useful to most people, which is you're building an application and you need to use a database. How do I pick the right database to use for my application, right? I think there's three primary considerations here. So number one is the data model or API, or like how do you interact with the database and what types of data does it support? Then there's the consistency model, which is basically what guarantees does the database give you about the operations you're performing on it. Kind of part of the API, but a different part. And then the third is performance and scalability. You need to be able to make my database scale to the size of requests I'm doing, to the data size, to the latencies I need, all that kind of stuff. So first, let's talk about data model. And to start, I want to go through kind of like the different storage abstractions that exist as kind of generally useful things when you want to store data somewhere, right? So the kind of lowest level abstraction is, a hard drive, a disk, a block storage device is the general term for it. And this is not something most of us directly program against, right? Kind of the higher level API that was built to make this a little nicer is file systems, right? Where it's kind of more a stream, it's still like a stream of bytes. It's not a like logical data type, but it's a lot easier to use, right? And since local file systems are obviously limited to one box, and also in the scale they can do, distributed and networked file systems were built, like NFS and Hadoop distributed file systems when I worked on, right? And then continuing this trend, there's also other kind of just bag of bytes systems like object stores, like S3, that are still not necessarily the most friendly API for a lot of stuff you want to do, but they're very scalable and performant, right? And then kind of the next abstraction level up is the like record or row abstraction, which is databases, right? And there's a ton of different types of these. You've got your relational databases, your document databases, and there's a bunch of different types. We don't have time to cover all of them. But this is generally the layer you're going to interact with as an application developer, right? So I wanted to focus on this, but it is also helpful to understand how these other layers work. because that'll help you understand the performance and behavior of the database you're using. So just to go over a couple types of databases and data models, there's relational databases, or SQL databases as they're sometimes referred to, which use structured query language or SQL to interact with your data. Like you'll define your data in terms of a table, which is a collection of typed columns, right? And then you can perform queries on that data. And so some of the reasons you want to use a relational database are, well, the primary is it handles relations, right? It handles data models and types of data where you have many different types of things you need to store and worry about how they relate to each other, right? For example, if I'm Amazon, I need to worry about orders and people and products, and all these things are very connected together, right? And the other thing is it handles obviously these common types you can define for your columns, like strings, integers, all the stuff you need in data modeling. And you can define complex types of queries in SQL, like joins and aggregations and other types of queries that are difficult to do in other databases. But the downside is, in order to define these relations and have the database understand them, you need to have a fixed, explicit schema telling it for every single thing you put in the database, what its data type is, and you have to define this up front, right? And because of this, generally these systems are built, not always, but generally they're built on a single host, because when you have all these relations, doing them all on the same computer is a lot more efficient than managing them across many computers. But that limits the scale these systems can typically go to. And some examples of these types of systems you might have heard of are, MySQL, Postgres, Oracle, SQL Server. These are all some common relational databases. Then we have document databases, which are kind of like, you can almost think of it as like every record is JSON. It's basically a hierarchical document of many different types of data. And so in these, it's a very rich data type that supports, like JSON, pretty much anything you could want it to, right? And it's both a pro and a con that you don't need to define the schema up front. It makes it a lot easier to load data into it. But then when you're querying it, you have to know the database won't tell you what data is actually there, right? What the types of your data is and what fields are present in your document, right? And generally, these only support like single document queries. So this makes it more limited in types of things you can do, but also means your database is easier to scale to a larger size because you can break your documents up easily across many servers. And MongoDB is probably the most famous example. So slides are going. MongoDB is probably the most famous example of this, but Couchbase, and there are other examples of this type of database too. And then key value stores is the final type I want to mention today. There are many more, but it's a much simpler API. It's kind of like a dictionary or a map where you have key value pairs, right? You can insert a key value pair into the database. You can get the value for a key. You can delete a key, and sometimes you can get like a range of key value pairs, right? So this is a very simple API, so it's super easy to use, and often also makes it easy to scale. But because it doesn't have any sort of type support, you often have to build that on top of it if you actually want to use it, right? And because the API is simple, what you can do with it out of the box is more limited. And so Foundation DB, which I work on, is an example of this. There are other key value stores like Cassandra, HBase, and Dynamo are examples, and they have some additional support for data modeling on top of the key value pairs, but fundamentally they're just key value stores under the hood. Right. So, that was a brief overview of some different types of databases, and you can see that how different types of databases might lend themselves easily to different types of applications, right? So now I want to talk about the consistency model for the database, which is something y'all might not be as familiar with, which is basically what guarantees the database provides. Sorry, Sanskar, what's that?
Yeah, we can take a question before we move.
Sure, we can do a question, yeah.
Okay, so relational databases support JSON data. So is there a case where SQL database should be preferred over NoSQL database for schemeless data?
Yeah, it really depends. Because the way relational databases implement is it's still a column within the relational database. You still have all of the other relational stuff. So if you need that, relational database is great. But often when you have a database that's focused just on one particular thing, it can do that particular thing a lot better than something that's more general, right? And that's the case of a lot of document databases. They're built around having documents specifically, and there's certain performance optimizations and features they can implement that aren't supported or aren't as easy to implement in relational databases, if that makes sense. And so generally what you want to do here is you want to look at performance benchmarks and see what can my database actually do for this type of data, right? That's when you want to look more at non-functional requirements like scale, performance, and as I mentioned, document databases can often almost scale larger than relational databases can. So
Makes sense. Right. So people have pointed out that you left out Redis for key value store databases.
yeah, I only had one slide for each type, or I put one slide for each type. There are hundreds of databases, right?
Right.
And there's a bunch of things I didn't mention. And Redis is also has its own data modeling on top of a key value store. Like it has types, it has other stuff too. So it's not, I had to summarize. And the intention of this talk is not to cover everything in the field because we would be talking for hours and hours, right?
No, I think people really like Redis probably because we have
Yeah,
one more.
it's a popular one. Yeah. Well, maybe I should have included that in my slide then.
George didn't forget about it. Yeah.
No.
Okay.
I also
Cool.
tend to think of Redis as more of a cache because it's often used for those type of cases. But yeah,
So is there another one called lake houses?
lakehouses that's a type of data platform, not as much as a type of database. But yeah, we can talk more about kind of those high level abstractions if you have more questions after the talk if you want, because this is a whole other topic besides the databases, right? These data platforms and how they enable businesses to do stuff.
Right. And there's Nadeem from Afghanistan. He's saying that he has some net electricity issues.
Oh,
So Josh will probably drop a link of his slides in the comment section after the live stream, and then everyone who wants to refer to it, they can go and like read it from
yep.
there, right?
I believe this will also be on YouTube after as well.
Yeah. So this will stay on YouTube and on LinkedIn as well. So if you
Yeah,
want to watch it again, you can just go on any site and then watch it again. So
it
that
sounds good.
works.
Yeah, and I'll be posting the slides and some resources for
Right.
reading up more on distributed systems in the chat afterwards.
Yeah, sounds good. So all of you can refer to it later.
Awesome.
Okay, we can move forward, I think.
Yeah, let's keep going. So consistency model, and some of y'all may not be as familiar with. So I want to do just a basic example of two different types of consistency models to show you why this is kind of something important and why this can really influence how you use your database. So the two I want to cover are strong consistency and eventual consistency. So in this example, to keep it super simple, I want to use a in-memory single process key value store or a map or a dictionary, right? So in this case, we're going to instantiate our database. We're going to set the key A to the value 1 and then read the value of the key A. In a map or dictionary, you would expect to get 1 for this code, right? And that is an example of strong consistency, which is that if I write or modify a record in my database, if I then go and read that record, I'm guaranteed to get the value I wrote or a more recent one that someone else wrote in between, right? And this is kind of the intuitive model, and it makes it easy to program against, right? So then what's the alternative? Well, eventual consistency is one. So again, we say we do the same sequence of operations, insert A equals 1 to our database and then read the value of A. We might get 1. We might instead get that there is no value of A, right? And then what if we tried to read again later? We might later get 1. We might still later get nothing. And there's not necessarily a bound on how long it takes before we read 1, right? So that's what eventual consistency provides, which is after I update a record, if I read that record, I'm eventually guaranteed to see the value I wrote, but not necessarily immediately. And at first glance, you might be like, well, this seems useless. Like, why would anyone want to use that? So first, there are some cases where this is totally fine, right? Like say I want to just have a rough idea of how many people are using my website right now, right? And every time someone goes on the website, I write a record, and every time someone leaves the website, I write a record. It probably doesn't matter too much if I see the number 1 million or 1,000,002 there. I still have a good rough idea of how many people are on the site, right? Another example is like personalization type data, right? Say I'm on Amazon and I want to, Amazon wants to recommend me stuff to buy. If I've made 1,000 purchases, it probably doesn't really matter for the output of the recommendation algorithm whether it includes the last thing I bought or only just the previous 999. It's still going to have a good idea of who I am and what I want to buy, right? So there are some cases where you can tolerate eventual consistency. And then the reason you might want to do that is keeping data consistent is expensive in distributed systems. It costs CPU, it costs coordination, and it's non-trivial. So generally, eventually consistent databases tend to be faster and more scalable than strongly consistent ones. So this is an example is what you have to do is you have to look at your data model and your requirements and figure out what consistency model you need, and then given that, what the best database to use for performance and non-functional requirements is. So just a brief overview of other types of consistency models. There's session consistency, which is a strong consistency for one user for the time they're using your site, right? But not across many users. An example of where this might be useful is, again, Amazon. Say it's my shopping cart, right? Amazon needs to maintain everyone's shopping cart, but I don't need to read or write anyone else's shopping cart but mine, right? So in this case, it doesn't matter if the database is consistent globally. It just matters that my updates to my shopping cart are consistent, right? And you can imagine that since there's this kind of relaxed requirement of the entire database not being consistent, a session consistent database might be more efficient than a globally strongly consistent one, right? And then there's other stuff like read committed, which is basically like if I'm reading a value, I'm guaranteed to read something that was committed, just not necessarily the latest one if there are multiple updates. And there's a ton of other consistency models, and I've linked some resources for that at the end. But basically the thing to keep in mind here is clearly what consistency model your database supports greatly influences how you can use it and what types of things you can do, right? And also greatly influences what kind of performance it can provide. So understanding this and reasoning about your database's consistency model will help you build the most effective application for your data. And the last thing I want to talk about is performance and scalability. And this is also a very deep topic, so I want to just cover one quick aspect of it, which is that some databases can scale in different ways, right? So, say I have my database, like we talked about earlier, saying, my CPU on my database is constantly at 100%, or my queries are getting slower. I need to make my database bigger, right?
Yeah.
What can I do? Well, number one, I can scale up, which is basically just to buy a bigger server, right? With more disks, more memory, more CPU, all the resources I need to do my queries. And this is often simple, right? And it works pretty well when that works, but there are some limits. Still, if you only have one computer, you're bounded to whatever the resources you can afford or you can get for a single computer, right? And then there are other things that within databases don't necessarily scale infinitely as you add more resources, right? Like an example is databases often have to lock data to deal with racing updates to it. And so if you lock a data item, only one CPU core can operate on it. You can't have 100 or whatever all operating on it. So the alternative is to scale out or scale horizontally, which is to add just many more instances of your database, right? And then to do this, you have to break your data up so that not every server has every copy of every data, right? And this is called partitioning. So the advantages here, obviously, you can scale past the limits of any individual machine, right? And we have fault tolerance, right? In our single host case, if that host goes down, our database is down, right? But in the horizontally scaling case, if I have multiple replicas or multiple copies, or each row is stored on multiple servers, then if I lose one, I can continue operating because I can still access it and update it on those servers, right? So this makes our system crash fault tolerant, right? The downside is it's not supported by all databases. As I mentioned, many relational databases are designed to not be able to do this. And also, when you have to break your data up so that not every server has every data item, this creates problems and is difficult to do effectively, right? And the other thing is that multi-replica consistency adds overhead, right? Every time I update the database, if I have to tell 3 servers instead of 1, that's 3 times the work, right? So it's not necessarily as cheap or as efficient. So I want to wrap this up with just a real-world example of, given some requirements, how you choose a database and how that choice changes over time. This would be a good time to pause for questions if we have any. This is the last section.
There is a real world example, like a real world question. Ashish has asked that sometimes the display of count of comments on a post and the actual count of comments differ. Is that an example of eventual consistency?
Yep, exactly. Yep. That's either an example of eventual consistency in the database, or it's an example of they might store that in a different database, right? They might have a counter database and a actual post database, and those individually might be consistent, but the overall experience is not strongly consistent, right? But yeah, that's a great example of that type of application or that type of consistency.
Yep. Another question from Flavius. What is the best open source RDBMS for multi-master application and why?
That's a good question. I feel like this is like everyone's going to have a different opinion here. I don't know. I feel like multi-master application is something that's really tricky, right? Because getting that consistency right, especially across regions, carries a huge performance benefit. So I'm assuming you're probably talking about like multi-region, because generally multi-master within a single region for RDMS and relational databases is not what you do. Typically, there's one primary and several replicas. I think Cockroach is a pretty common database that has a multi-region replication that's supported for open source. Obviously, there are databases like Spanner at Google that supports strongly consistent multi-data center transactions, but those are not open source because Spanner is a very proprietary system. I think Cockroach is pretty good. There are others. Yeah, I guess I'll say Cockroach because that's the one I'm the most familiar with.
Okay. Another question. Any relational database that supports horizontal scaling?
Yeah, so some of them do for sure. And generally, so what some companies do, like Facebook, for example, which we're about to talk about, they run a bunch of different instances of MySQL and they build the horizontal scaling and the partitioning as their own data layer, right? This is also what PlanetScale does. Their service that provides like MySQL as a service, basically. But there definitely are other ones, like Aurora, for example, is an example of a database Amazon built that has like the relational API, but it internally scales horizontally and is multi-region or multi-availability zone consistent. So there are certainly ones. In open source, I guess, I mean, FoundationDB is a database I work on that it's not SQL support, but it does have transactions and it does scale horizontally. So there are certainly databases out there that do it.
Makes sense. Okay, I think we can like move forward and then take the rest of the questions later.
Yeah, sure. All right, so this real world example I wanted to talk through is how Facebook Messenger was built, because I worked on a project adjacent to this when I was interning there. So Facebook as a whole was originally built using MySQL as the database, right? Because MySQL and PHP was like the common starter kit, you know, when Zuck was in his dorm room building Facebook, right? So that's what everything started on. And then what Facebook wanted to do eventually was add inbox search for Messenger, right? And this is a very different workload than just normal Messenger, right? Normal Facebook Messenger, you're just generally looking at the last couple messages. You're usually not looking at the history, right? Whereas inbox search, you are explicitly looking at the whole history. And you're looking at it in a different way. You're not looking by time, you're looking by keyword, right? So it's a very different workload. It requires more horizontally scalable database and one that supports more writes than MySQL does. So Facebook built Cassandra, a new NoSQL database, to try to address this. But then Cassandra didn't ultimately work out for them because it was costly and the write-heavy performance, they couldn't get it as good as they wanted. So instead, Facebook was migrating to Hadoop for their analytics platform, and Hadoop comes with a key value store called HBase that is horizontally scalable and does support write-heavy workloads. So instead, they migrated Messenger and inbox search to HBase. And when I was there, I worked on Hadoop Distributed File System, which is the storage layer for HBase. And so this worked very well for a number of years. But then Facebook decided to build a new database, essentially. Their graph database, Tau, was still using MySQL. They were just doing their own partitioning manually on top of it. And what they realized was that its storage engine, basically the way the database translates the data on disk, was inefficient for what they wanted to do. So they built a new storage engine while maintaining the same database API. The storage engine was called RocksDB, and they called the new MySQL version MyRocks. And the primary reasons they did this were cost, essentially. It was just cheaper for them to store this data in a different way, right? And so then when they did this, they had the system already. They realized that, hey, this would also be cheaper and better performant than HBase for Messenger. So they migrated Messenger from HBase to MyRocks. And so this is kind of that whole story. And the reason I wanted to walk through this is to see an example of how both functional and non-functional requirements go into what database you choose and how that can change over time, right? So that's kind of to take away from this whole section. The kind of main things I wanted to mention are, when possible, go with the simplest and easiest system that works, right? When Zuck was in his dorm room building Facebook, he wasn't thinking, I'm going to need a horizontally scalable, multi-billion user database, right? He was like, MySQL and PHP, it's easy, it works, we can iterate quickly, let's do that, right? And then later you can migrate, and that's what they did. So go with the simplest and easiest system that works. That'll let you iterate the quickest and avoid problems. And then the other big thing is, as we saw, most of the choices after the initial system choice were based on non-functional requirements changing, like cost, data size, availability, latency, throughput, like performance considerations, not application requirements changing, right?
Okay.
And then as we saw through just kind of the slides earlier, using the right data model and API makes your programming a lot easier. If your data you're trying to store naturally maps to that. And then just really be aware of the details and gotchas of whatever consistency model your database provides. So these are the resources I'm going to send out after the talk. And that's all I have. Thanks so much for listening, y'all. Hopefully it was informative, and I'm happy to answer any questions that we have.
Okay, I feel like I've, you know, like I've gained so much knowledge from Josh, and I hope all of you also feel the same way. So if you really like the talk, you can like now ask questions to probably like solidify the knowledge that we have gained today.
Yeah,
So if you have any questions at all, you can go forward and ask them.
yeah, for sure. Yeah, I'm happy to talk about anything that's kind of deeper dives into these topics or just stuff we didn't get to. So Redshift is interesting. Redshift does sort of scale horizontally. You have to, I guess the key thing with Redshift is you still have to like provision a bunch of instances for Redshift. So like it obviously scales has a single host, but it's not as elastic as other data warehouses you might be able to use, like Snowflake, for example.
Right. So another question, how to handle the increase in concurrent connections of the application in the
Mhm.
special cases like functions and etc.
Yeah, so that's kind of goes back to the other question earlier of like how do you tell when you need to like scale up your system? Like one we talked about like CPU and latency, but another metric you can use is like outstanding connections or like concurrent connections. Whether like, that has some overhead in terms of network connections because each network connection has to take CPU to maintain, has a file descriptor on the process for the connection and all of that. So generally, what you need to do is you just need to scale out when you have an increasing connection, so you can spread the connections across many servers. Or scale
Makes
horizontally.
sense. I hope you got that, Parvati Rajan.
Mhm.
So another question from Ashish, who's listening very intently and asking a lot of
Yeah,
questions,
appreciate it.
which we really like. So yeah, all of you can also ask more questions.
Mhm.
Can you explain what is sharding?
Yeah, so sharding is another term for partitioning, which we briefly talked about, which is basically that I have a horizontally scalable database. How do I spread my data across those servers in an effective way, right? And there are usually kind of two common approaches for this. One is range-based partitioning, right? Well, so you might have like consider like all the words in the dictionary as a data set, right? I can say, all words start with A, go on this server, all words start with B, go to this server, and that's kind of your range partitioning, right? And the reason you want to do that is because if you're doing queries for ranges of data, those ranges are stored together, so it's efficient, right? Um, but the problem with that then is if certain ranges are more active or busy than others, you can kind of hotspot or like focus the load on certain servers in your cluster like unevenly, right? So the other main approach is what's called like hash partitioning, where you basically just use consistent hashing to assign each data item or set of data items to a server, right? And the issue, the positive there is you don't have the load imbalance problems because your hash algorithm is ideally uniform, but then you don't have the range affinity you need for doing like range queries, right? So those are two examples of how you implement sharding, but overall it's just the term for how you distribute data across your horizontally scalable database.
Makes sense. Okay. So we have a question from Aditya. If my code is running in a distributed server, how do I trust that what network call I am doing, that he is getting the correct data, as a malicious server can intercept the request and send incorrect data?
Yeah, so that's a good question. So I think there's several mechanisms. So number one, you can make the database protocol handle like Byzantine failures like this, right? But that's kind of more expensive. So generally what most companies do is this is more of a security problem, right? Is you want to have like security practices in place to prevent any sort of malicious server from being in the request path, right? So for example, I can, make a security perimeter such that only authorized users can log into my network. I can use security measures such as encryption, for like encryption over the wire for like TLS, so that messages you send are encrypted and can be validated that they weren't tampered with. I can do encryption at rest to make sure the data my servers are storing is also only readable by authorized parties and not encrypted or not tampered with, right? But yeah, it's basically a security problem, and there are protocols you can use, and there are features you can use in the software in like your databases to enable this. I think for this particular case, TLS or transport layer security is what you want to use. And basically encrypt every message you send over the network, and the decryptor will be able to tell if it was tampered with or it's invalid.
Makes sense. So yes, people will. This event is recorded, so you can always come in later and then watch it anytime you want to, because it might be a lot of knowledge to take in at once as well. So you can come in and then
Yeah.
watch, and you will also get the slides from Josh and
Mhm.
other resources. So yeah, it's like a holistic learning experience. So uh, Giriraj asks, how do you select between Nginx and HA proxy? Like, do you have a preference also?
Yeah, I pretty much I like Nginx. I haven't used HA proxy much, so I'm probably not the best person to do a breakdown of this. But I mean, in general, when you're selecting a load balancer, or sometimes Nginx and HA proxy are examples of other systems that have additional capability, like reverse proxies and stuff. It basically just depends on like the features they have, the performance they have. Again, like sometimes non-functional requirements. There are performance benchmarks that can show like the performance of different load balancers. Yeah, I haven't actually had to make that architecture choice in the system I built, so I can't tell you what I've done, but I've done that for similar systems, and those are the kind of things you take into consideration. Like, and HA proxy and Nginx might have different load balancing algorithms they support, might have different like ways of health checking, might have different protocols they support, like HTTP or other proprietary protocols, right? So there's a lot of things that can go into it.
Okay, so we'll take a last few questions and then we'll wrap up the entire event. Okay, so Mustafa asks, in CQRS pattern, can you give an example of how reading and writing is separated, for example, in database operation, and wouldn't that introduce race conditions?
Yeah, so I think CQRS, I think you're talking about like separation of reads and writes. I think what that stands for. So it depends on the system, right? Like the way databases handle this is like they have their consistency model, right? It's basically one other way I would say to how to reason about consistency models is how racing reads and writes are supported by the database, right? Strong consistency, racing reads and writes have a very well-defined behavior of what a read racing with a write will see and when it will be able to see that write, right? So basically, you have to handle these race conditions, and how you handle them is your consistency model. So like, for example, in strongly consistent databases, often what they'll do is there'll either be a single kind of owner of a data record, and so if I'm updating that record, that owner can enforce whatever relation or ever like kind of ordering I want those to have, right? And generally you can do this via locks, or you can do this via like multi-version concurrency control. Like there are a bunch of mechanisms that databases typically use to enforce like certain types of behavior to happen during race conditions, right? So like, for example, if I'm updating a row and there's a read that's going at the same time, I can lock that row for the writer to make sure that no one reads it while I'm updating it, right? Those are types of things you can do to support this. Hopefully that answered your question. If not, let me know and I'll try and
Yeah.
rephrase.
Then let Josh know if it didn't answer. I think it did answer your question. Okay, so another question. If you have a key value store, how do you choose a good key to avoid performance problems?
Yeah, so I would say that in a key value store, it's kind of the same as the problem as selecting your primary key in a relational database. Like you basically need to choose a key that effectively maps your data to the type of queries you want to do, right? Like say I have a system of like logs and I have a query by time. I want to make my key the time so that I can have like ranges of time together. And this basically goes down to the partitioning problem we were talking about actually, is if the type of performance you want is efficient range queries, you want to use generally range partitioning, right? And then structure your keys such that keys in the same range get partitioned together, right? So yeah, it's basically, it depends on your application and the database, but I guess the general things are you need to consider the data model, you need to consider how your database is partitioned, and then you need to consider the types of queries you're doing so you can make your key support those efficiently. Because the other way to think about a key value store is there is a single primary key index and there are no secondary indexes, right? Because in the relational databases, if you want to query your data a different way, you can just build another index on top of your data that makes that query efficient. But in a key value store, you get one index and that's the key. So you have to really think about how your data is going to be used and build that key effectively. Yeah, thanks for the question.
Okay, I think we can like wrap the questions. If you all have any other doubts or any other questions, you can always reach out to Josh on LinkedIn, and then I'm pretty sure I'll be happy to answer any doubts that you have with the topic, right?
Yeah, for sure.
Okay, so redirect all of your questions to Josh's LinkedIn messages now, and then he'll answer all of them to you.
Sounds good.
Right. Okay. So let's conclude the live stream now. I just have like one final question for you, and that's for everyone in the audience here. So everyone who's just starting with the journey with distributed systems, what is your three top piece of advice for all of them?
That's a good question. Yeah, I guess it kind of depends on where you're starting your journey, right? Like for me, for example, if I'm a college student, one of my best ins to the field and best resources is classes, right? In addition to your college may be offering classes, there are some pretty good online classes you can watch about distributed systems and databases. And for example, Carnegie Mellon has a really like well qualified, well regarded database class that's online, and they post all their lectures there. Or if you're attending a university, your college might offer that class. And then the other thing, like for me, is if you're in college, internships, right? Generally, if you're hiring for like a principal or senior software engineer for a database, they're going to want database experience or something very close to it, right? But if you're an intern, that like experience level bar is not there. Like they're specifically looking for people who have not done that, right? So then things like having projects that show you are familiar with things in the field, or taking classes, or kind of that you're in there, right? But if you're not a student, or that's like not a route you can take, there are obviously other ways to get into the field as well. I think no matter anyone, I would just recommend there are a ton of resources online, blogs, books, and I'm going to post some of these resources as well. But then, so if you're already in the industry, I think the way I've seen people have success is either start contributing to open source projects that are in this field, or start working at a company like adjacent to one of these types of projects, right? If you want to work on databases, work on projects that use databases very closely and effectively. Like for example, Indeed, my last job, there were multiple people who were we were building a proprietary database, and there are multiple people who joined our team to work on the database after previously being customers of it, right? Because when you're a company and you're looking to hire, especially for a proprietary database, someone who's already used it, understands the system, and is able to reason about it already is a quicker person to onboard, and probably a good signal the person might be a good fit for that team than someone random, right? And then the other thing is open source. You can either just kind of go to an open source project and try and contribute, or I've also found success like contributing to open source through my job, right? Like at Indeed, for example, we were building, our system used Zookeeper, which is an open source coordination and consensus system to store our metadata. And then as we're using it, we built some like interesting client functionality and utilities that were not in open source. And so what I did then is I open sourced those into Apache Curator, which is an open source Zookeeper client. Right, so basically built something interesting and then contributed to open source as a part of your job. That's another avenue in. So I guess I would say the top three are read stuff online, contribute to open source, and find a job that at least lets you work adjacent to, if not on, these types of systems.
That's very good advice, and I think that applies to literally everything that you can do.
Yeah.
But yeah, so if you're in distributed systems, do everything that Josh has done and then like has suggested. And then yeah, I think this was an exciting live stream. I got to learn a lot from Josh, and if you all did too, you can always appreciate him in person, or even drop in the comments below so that he knows that a lot of people have watched it till the end and they have really enjoyed the live stream.
Yeah, for sure.
Right. So
Awesome.
any closing thoughts?
No, I mean, I think we talked about a lot today. I guess the closing thoughts are just, I think no matter what type of software you work on, understanding these fundamentals is really important. It'll help you build better software systems. So yeah, thanks so much, y'all. It was a pleasure to be here, and I'm happy to talk about this stuff. And thanks so much for coming.
Thank you so much for giving us your time, Josh, and like going through all of those slides. And thank you so much for being there.
Yeah.
And thank you so much everyone for coming to view our content, and then who really appreciated whatever
thanks so
Josh
much.
spoke to today. Yeah. Okay. That's it.
See you.
That's it. That's the end. Okay.
Have a good one, everybody. Thanks.